This presentation is delivered by the Stanford Center for Professional Development.
Yes, we're on. Okay. Hello, everyone. Welcome to 16th Annual Christmas Tree Lecture. I don't know how many of you have ever been at a previous Christmas tree lecture? A few, okay. I do see a lot of friends here, too. So the idea is that every year about this time, I try to give a lecture about the coolest thing I learned about trees during the year. The trees are the sort of computer scientist's best friend, and so every year there's always something new to say. And let's see, the title today is Why Pi, and I learned just an hour ago that my title wasn't as original as I thought. Let's go to Google and see this here. By the way, before I forget, I have to say that today is a very special day for me because I just finished. Let's see how which program am I talking to? Safari here. Okay, I got to move this over. Okay, so I just finished. Actually, for the first time in my life, and probably the only time in my life, I finished 2 books on the exact same day, and exactly today, this book, Selected Papers on Fun and Games, is going off to a printer in Chicago, and another book called The Art of Computer Programming, Volume 4A, is going out to a printer in Massachusetts. So it just happened that both of them are taking place today, and so I'm quite kind of celebrating, and also I'm going to have to go into input mode instead of output mode for a while because the total pages are, let's see, there's 900 pages in the Art of Computer Programming and 750 in this one. So I'm about paged out now, but it took me many years to write these books, of course. Okay, so now let's go to Google and let's try the title Why Pi, because I thought it was original, and I never even checked to see how it was. But it turns out there's lots of things, even I don't know, stuff about I think that we did get. Yeah, we did get a little bit about it. Okay, so and so here's where you find out that actually this people have been tweeting about it and so on. So maybe out there in Webland there are a huge number of people. Who knows? Let's hope it doesn't crash Stanford server, but we'll see. So why pi? Let's say, first of all, why does pi relate to trees? So many times in the past, I've talked about the number of trees that you can do with n nodes. So let me see if we can get onto this other device here and see how the notepad works. You switch to this guy. Good. For example, there are two trees with 2 nodes, actually forests, let's say. This is one, and this is the other, where this just means the forest consists of 2 separate trees, but each tree is just a root and nothing else. But here's a tree that has a root and one descendant. So there's two of them when n equals 2, and of course only one when n equals 1. 2 of these forests. Well, when n equals 3, there's 5 of forests. There's this one, which is 3 nodes all by themselves. Then there's this one. We also consider this to be different because they're ordered. And then there's something like this, and one more. Anybody think of another one? What? Sequential? Yeah. This going all the way down. Okay, so there's 5 then. Okay, so the number of forests with n nodes is called the Catalan number. It's very famous. It occurs in lots of places, and so what happens is actually I might as well make a table here. we should start at 0 instead of 1. Let me see. I got to learn the zooming feature too. So we start at 0 and then 1, 2, 3, so how many forests are there with 0 nodes? There's 1. Okay, and there's 1, 2, 5, and then it continues on 14 and so on. Very fascinating sequence of numbers. And there's a formula for it, and that is 2n factorial divided by n factorial and n plus 1 factorial. Now, I better explain what a factorial is, although if you've never seen factorials before, it might be, you might have a lot more questions than if you have. But, so, for example, n factorial is just the product of the numbers 1 up to n. And 0 factorial is the product of all the numbers 1 up to 0, which is empty product, so it's 1. So let's check it out when n equals 3. That would mean 6 factorial over 3 factorial, 4 factorial. So that would be 1 times 2, 3, 4, 5, 6. And then we divide by 1, 2, 3, and then 1, 2, 3, 4. And so the 1, 2, 3, 4 cancel, and this 1, 2, 3 cancel with the 6, and so it comes out to be 5. That's the formula. Okay. Now, but pi gets into this too, because it turns out that this is approximately 4 to the n over the square root of pi n n plus 1, let's say. I could also write square root of pi n. Okay, so now, for example, well, let's check it out on the internet, because I got to learn the technology of this lecture room as I'm giving this lecture. So I'm going to go to my computer now and we're going to try something else. Let's see. Yeah. Okay. So I might as well go to Wolfram Alpha. Okay. Okay. So now, okay. So we say let's take n equals 1,000, right? So 2,000 factorial divided by 1,000 factorial. Sorry, and then also they divide by 1,001 factorial. Okay, so there we go. This is the number of forests on 1,000 nodes, and let's see what it says. Okay, there it is, and it's approximately, you see, 2.046 10 to the 597. Okay, okay. Now I'll spawn another window and try to get Wolfram Alpha on that one too, and now we'll try the other guy. Yeah. Okay. So here, 4 to the 1,000 divided by the square root of 1,000 pi, and divide that by 1,001. Okay. So let's see what. Okay, so let's see how close we got here. Is that working? How can I make okay, so yeah, I'm going to scroll this up. Sorry, I should have practiced this beforehand. But I just want to get that guy there, right? And then I want to bring the other screen up and shrink it or something. Let's see, what can I do here? Why did I get help from Adobe on this? Who knows? Okay, so anyway, it's not going to certainly match to all those places, but it should match pretty well. So let's see what we do here. Okay. My talk should be why didn't Knuth practice in advance? Okay, so here we go. 20461 1055, 20463. Okay, well, anyway, the leading digits are right, okay? And if I hadn't put square root of pi in there, it wouldn't have been so close, of course. And we could try it if we had more time with 10,000 and 100,000 and so on, and we'd find out that somehow pi has something to do with trees. Well, this has always been a mystery to, I think, to everybody, why pi should occur in connection with forests. It just seemed to be one of those strange coincidences of effects of nature that, well, there's a constant, and lo and behold, it agrees with pi to any number of decimal places, so it must be pi, or square root of pi in this case. Well, however, 2 years ago, a guy in Sweden named Johan Westland figured out why. And or he published why, and it's kind of, I'm going to write his name down because I think he's watching from Sweden at this very moment. I mean, it's the middle of the night there, but still, he said he was going to try to watch, and so I'm really nervous. I hope I get this right, but he published this in the American Math Monthly. Was it December 2007? Well, I said 2 years ago. I'm sorry, 3 years ago. And it's on pages 914 and 917. And so he's yeah. So his article. Actually, I didn't see it though until a year later because I'm always a year behind reading stuff like this, and he figured out, I think for the first time, a reason why circles have something to do with factorials, and so I'm going to try to explain that now. And fortunately, it's really not that complicated. So it's quite beautiful, and I asked him how did he ever come up with this. So he told me that it was actually 6 years ago. He was trying to figure out some questions to ask on the Swedish Math Olympiad, a test for high school students in Sweden, and so he was thinking about a problem that Paul Helmus had mentioned in his book. Paul Helmus has a book called Problems for Mathematicians Young and Old, and one of the problems that Helmus asked was this. Suppose you could take you design a die that wouldn't roll each face of the die with equal probability, but instead it had 6 faces. But it worked out that if you rolled 2 of these dice, you would get the numbers 2, 3, 4, up to 12, all with the same probability. And that, so Helmus said, is it possible to work that out? So let me show you what that means geometrically. If I can, I guess I got to now come to another thing. Let me go to preview here. That should be good. Okay, so preview file, open. Okay, so now let's see, desktop, Westland Pi. Here we go. Westland. Okay. So page 1, please. Okay. So here's the deal. I got 6 probabilities for the 6 faces: P1, P2, and so on up to P6, and I want somehow the probability of getting the same P1, P2, P3 also occur on this other axis. I should probably put them there too. And so the probability that I get 2 1s is P1 times P1. And so this big square here, that's the area of that is the probability that I'm going to roll a 2 if I roll 2 of these dice. Then to roll a 3, I have to get either a 1 on the first die and a 2 on the second, or a 2 and a 1. So this rectangle plus this rectangle is also supposed to turn out to be the same area, as the other two. And in fact it is. I can tell you now that if you call this a square, then this is just half as, P2 is half of P1. And so you add up these two guys and you get the same area. And so then he also wants these three squares to add up to be the same, because this is the probability that you shake a 4 with two of these dice, 1, 3, or 2, 2, or 3, 1. And so on. And so this purple guy here is the probability that you shake a 12. It doesn't look like it's going to make it. But anyway, in Helmus's book, he gives a tricky proof that it's impossible to design dice that would do this. But it's a complicated. It's a proof that's it's sort of nice and short, but it uses it uses complex numbers and unique factorization of polynomials and things like that. Johan was saying, well, maybe high school students would approach a problem a different way, saying if we're going to try to make these rolls all come out equal, what do we have to do? So let's see what it means. So it says that P1 squared is going to have to equal P1 P2 plus P2 P1. In other words, that's going to mean that P2 is going to have to equal 1/2 P1. Okay. Then let's try. It's also going to have to equal P1 P3 plus P2 P2. This is the probability of shaking a 4. P3 P1, and that's equal then, of course, to P1 P3 plus 1/4 P1 squared plus P3 P1, and so we have to solve that, and it turns out that's going to mean that P3 is equal to 3/8 of P1. Factor of P1 out of all of these, and you get P1 equals P3 plus 1/4 P1. So there you are, 3/4, half of 3/4. And so on, P1, P4, up to P4, P1, and you work it out because we've already figured out what P2 and P3 are, and it turns out that P4 is equal to 35 over 128 P1, and sorry, that's P5. P4 was 15 over 16 of P1, and P5 was 35 over 120. Okay, so we get these coefficients, and now the interesting thing, if we're just playing around with it, is we see that actually we can do it at least up to this step. We can. This is for rolling 2. This is a 3, a 4, and so on, up to rolling 7. So we can make all of those 6 possibilities from 2 to 7 all equally likely, and it's unique. In fact, once we choose P1, then we know what P2, P3, and P6. Okay. Now, if we're going to go any further, then it's going to turn out that we just don't have any wiggle room anymore. So this will prove that it's impossible to solve Helmus's problem with a low-level approach instead of a high-level approach. But no, these numbers. Johan looked at these numbers, and they're kind of interesting. Notice that there's only small prime factors here. The denominator, in fact, is always the power of 2, and the numerator never has anything bigger than a 7 as far as the primes in it. So if you look at it a little more, this is 1/2. Then 3/8 happens to be 1/2 times 3/4, and 15/16 turns out to be 1/2 times 3/4 times 5/6. And you might notice a pattern at this point. What do you think P5 is going to be? Nobody gets it? Come on, shout it out. Yeah, shout it out. Okay, so yeah, okay, yeah, you see that we're just writing the numbers. We're not quite calculating the n factorial. We don't have 1 times 2 times 3 times 4. We're putting the even guys in the denominator and the odd guys in the numerator. But here we are, certainly a pattern that calls for further investigation. And so Johann started looking at the pattern, and he said, well, first of all, let's prove the pattern. But before let's see, yeah, we might as well verify that it works. And so what I'm going to do now is I'm going to say Pj equals Aj minus 1 times P1. I'm going to number. I'm going to not call it Aj times P1 because the formula for P2 had 1 term in it, and the formula for P3 had 2 terms in it. So I'm going to say there's J minus 1 terms in the thing. So I'm going to try to see what this is, and so A0 was equal to 1, and A1 was equal to 1/2, and so on. Then we had 3/8, and so now we form this infinite series A0 plus A1 times Z plus A2 Z squared, A3 Z cubed, and so on. And let's call this function A of Z. The reason I do this is because I'm going to square it and I multiply this series by itself. And what do I get? I get A0 for the constant term, and then the coefficient of Z is A0 A1 plus A1 A0, and the coefficient of Z squared is of course just what we were doing before, pretty much without factoring out the P1. Okay, so this is actually equal to 1 plus Z squared plus Z cubed. It's supposed to be 1 in every case. That's what these A numbers do. And so this is equal to 1 over 1 minus Z. That this infinite series is a geometric series, and the value is 1 over 1 minus Z. So great, because then I know what A of Z is. A of Z is plus or minus the square root of that. So this original series where we were trying to figure out what the little a's are happens to be the series for 1 over the square root of 1 minus C. And of course, I have to choose the plus sign here because I said A0 was equal to 1. The constant term is equal to 1. So this is it, and we have the binomial theorem that says that if you have 1 minus Z to any power, the answer is a series that goes up to infinity that has minus, let me write it a little slower. This is 1 minus Z to the minus 1/2 power. So you can always expand a binomial to a power, even when the power isn't an integer. And the binomial coefficients come up there, and it's minus 1/2, choose K, or let's use N, I guess, N times Z to the N. So in other words, A sub N is equal to minus 1/2, minus Z to the N. That was minus Z to the N, because I have minus Z instead of plus Z here. So the idea is then that A sub N is equal to minus 1/2 over N times minus 1 to the nth power. And so now you might not all be familiar with binomial coefficients when they're fractions like this, but they're actually quite simple. Here's what it means. Let's try A3, for example. A3 is equal to minus 1/2 In general, when you have a binomial coefficient, you start with this guy and then you subtract 1 and keep on subtracting 1 until you have n terms. And then you divide by 3 times 2 times 1. So this is the and then we kind of multiply this by minus 1 cubed. So that's what minus 1/2 choose 3 is. And I can get rid of the minus signs by changing all these guys to plus. So what I really have is 1/2 over 3, 3/2 over 2, and 5/2 over, right? So 1/2 times 3/2 times 5/2, and then the denominator I can write in the other order, 1, 2, 3 instead of 3, 2, 1. It's the same deal. So that's 1 over 2 times 3 over 4 times 5 over 6. That's the pattern that we saw. Okay, so we got it. Nice proof of that. All right, now, in order to, however, that just determines the ratio between P2 and P3 and so on and P1. We still have to make these things. These are supposed to be probabilities. We want P1. We want the sum of those 6 probabilities to equal 1. Okay, so this is supposed to equal 1, but this is equal to P1 times P1 squared times A0 plus A1 up to A5. And so in order to figure out what P1 is, I have to know what this sum is. What is the sum of all these guys? Well, that is very nice actually, because if I have any infinite series like this, and I want to know what the sums are of the coefficients, I just multiply the infinite series. Okay, so I take A of z and I multiply it by 1 plus z squared, etc., and I get A0, and then here I get A0 plus A1 z, and coefficient is z squared. I get A1, I get the sums that are there. Okay, so now actually I'm going to call this S1 plus S2z and so on, S3z squared, because I'm interested in S6 for the 6-sided dice. So the coefficient of z to the 5th is actually this S6 here. The sum of S6 is the sum of A0 through A5. And then going back to what I had, I said that P1 squared times S6 is equal to 1. That's the sum of the 6 probabilities. So I have to figure out what S6 is, but that's easy because we know that A of z was 1 minus z to the minus 1/2 power, and this thing is 1 over 1 minus z, so that's 1 minus z to the minus 1 power. So I'm left with 1 minus z to the minus 3/2 power. And so this is just, you see the summation of minus 3/2 to the n times minus z to the nth power. And the coefficients of z here then are just, again, coming out of the pattern. All right, well, so it's never easy to do math in front of an audience or to watch like this step by step. But really, this is the point is now there's going to be a great pattern on the sums of these numbers too, and in fact, here's what it is. So we started out. We had A0 equal to 1, A1 equals 1/2, A2 is 3/8, and so on. Now, if I add this together, S1 was equal to A0 is equal to 1. S2 is going to be the sum of the first two guys, and that's equal to 3/2. And S3 is the sum of the first three guys, A0 up to A2. And that, add 3/8 to that, and what do you get? This is 12/8, it's 15/8, right? Okay, so anyway, this is 3/2 times 5/4. And guess what? S6 is 3/2 times 5/4 times 7, 6, and 9/8, and we're going to have 5 terms in there, I guess. 11, 10. Okay, and so there's a nice formula then for the s's as well, the sums of these guys as well as the others. This is as hard as it gets as far as proving that pi gets into the action, but it's an easy pattern to prove by induction. However, this infinite series method explains why this pattern is really there and why such a simple pattern should occur in these numbers. Okay, let's see. But now I see people standing in the back. You know, actually there's some good seats over here if you want to come up. But also I wanted to mention that there's going to be a prize at the end of the hour for the person who asked the people who I got about 6 books there, and the people who asked the best 6 questions during the hour are entitled to these books. So may I ask if there's any questions at this point? Everybody understands so far what I've been doing. I'm going to give you another picture now so that we can take. Okay, so here, got to move now. Let's see. I didn't even need this. I might as well go here. So here I've got 10 instead of 6, and I threw out the guys that weren't going to be equal probability. But if I had a 10-sided dice, I could do the same thing, and I could make sure that all of the first sums of 2 things would have equal area, and the numbers A0 through A9, give me the sizes of these rectangles. Here's a rectangle that's A3 by A1. A2 by A0, and then the s's tell me the sums up to this point. So S10 is the width of this whole thing is S10. Now you see what the area of the red is 1. Now what about this brown? The total area of the 2 brown guys is 1 also. Each one is a half. And this one is 3/8, this one is 3/8, and this one is 1/4, and so that adds up to 1 also. So I got in the colored things here. I got 10 things each of area 1. So the area of these colored rectangles is exactly 10. You with me? But now, see, Johann noticed that it also looks very much like a circle. So here I have a circle of radius S10, and if we zoom in on this, we see that it actually is very very close to. So I've got these rectangles that are not only do the rectangles have nice expressions for how wide and tall they are. These fractions that we got, but also it's very close to a circle. You see what's happening here is that the circle is crossing over. All of these purple guys are getting cut exactly by the thing. It's always cutting that one. It's never getting into the blue. All right. Now, of course, this is only the case n equals 10. So let's see what happens if we go up a little bigger. Before I lose this slide, though, I want to mention one formula that is useful, and that is that Sn is equal to 2n times an. Nice formula. In other words, S1 is supposed to equal twice A1, and S2 is supposed to equal 4 times A2, and so on. So that looks right. And S10 would be 10 times A10. We didn't actually need A10 in this picture, but 20 times A10. But you know, if we had calculated A10, it would have been just 1/20th of this total width. So that's another way to get at these triangles. And so we sort of bootstrap to the next guy. So now let's take a look then at what happens if I zoom it down. So this was the case that we just looked at with 10, and now we could add another 10 guys in here, and so now we get up to S20, and this will be the area. The total area of the rectangles here is 20. What? Oh, hey, I'm sorry. Can you get onto my computer screen? Jason. Guys went to sleep, I think. Okay. Okay. Yeah, you got it. Okay. So yeah, this is okay. So here's the 10 that we were looking at, and now we can add another row of 10, and so we get 20 here, and the radius of this guy is S20 now, and now the area of these rectangles is 20, because each of these rings, in the rectangle wise, has area exactly 1, and it's also you know, then we get 30 and 40 and 50 and 60, and still if we look closely at the thing, it's you know, it's that circle is just cutting right in there. Each of the it includes all of the blue rectangles, the second from the top, and it's cutting the purple guys at the edge into parts, and then it's not. But the circle never, you know, well, it also gets a little bit into the white in the next level. Okay, so that's what happens then if n increases, and it looks like then that we got a really good approximation to the circle, and that's the next thing that we have to prove. Okay, so now there's a beautiful proof of that too. But let's take stock first of what we've done then. So we have I'm going to come back to my pad now, and what we've done is we have a rectangle of area n. And that is approximately equal to the area of a circle, and that's where pi comes in, because that's where the definition of pi. Well, there's two definitions. One is that it's the ratio between the circumference of a circle and the diameter of a circle, but the other equally good definition is it's the constant that occurs when you get the area of a circle, which is pi times r squared. So now here we have not a whole circle, but just a fourth of a circle. So n is approximately 1/4 of s n squared. And in fact, if we can prove that, how good is this approximation? If we can prove that that the circle always cuts the rim as we noticed there, so it's always coming through here. In every case, it's always on every rectangle on the edge. It's getting cut on the top edge and the right edge. Then this has to be less than n plus 1 and greater than n minus 1, because we got n minus 1 if we stay totally within this region, and we got n plus 1 if we add another layer to the thing on the outside. So so if I can prove this, that the circle actually has this property that it stays outside of the inner notches and inside of the outer notches. Here, here's an inner notches here, and the outer notches are these guys. And so if the circle always lies between the inner notches and the outer notches, then we have this nice formula for exactly how well the rectangles are approximating the true circle area. You got a question?
Aren't you missing a pi?
It was right there, but we just didn't see it quite good. Now, I would like to say that I did it on purpose to see if anybody was watching, but anyway, since you did that, why don't you come up afterwards and get one of these books up here? Okay. Any other questions? All right. Yeah, actually, that was, I guess your question was, why not pi? Why? Okay, so.
Overloading the notation n.
What?
You're also using n in two different ways.
Oh, I'm using n in two different ways. Yes? Is that bad? Yeah. So what is Sn? Sn is the radius. If I've done this construction n times. So in the last picture, n was 60, and S60 was the radius, and the area of the rectangles in that case was 60, because each rim has an area of 1. So it's okay to use n in those things. But if I hadn't, then I would have some problems because I have to relate. If this was Sm, then I wouldn't have proved anything. Yeah. Okay. Other questions? So now now we come to the cute proof that it actually it really does correspond to a circle. And so what I want to do is first I want to show the relation between S. Well, let's consider, for example, S9 squared and S6 squared. So S6 squared, let's see what S6 squared is. And well, let remind you what S6 is in the first place. It was 3/2. Let's see, I want to get it right. Yeah, here, 3/2 times 5/4 times 7/8 times 9/10, 11/12. What? 7/6, 9/8, 11/10. Good. Okay. It always ends with 2n. It always ends with 2n minus 2. Yeah. Okay. And S9 squared is going to be. Then I square this. Okay. So I square this each of these terms. So S9 squared is going to be S6 squared, and then we got three more guys: 13, 12 squared. 15, 14 squared, and 17, 16 squared. Now, I'm going to show that actually there's a nice relation between these things, and so what it depends on is the following. If I take a number that's 1 plus 1 over 2k squared, which all of these numbers are examples of that. K equals 6, 7, 8 in this case here. This is of course 1 plus 1 over k squared plus 1 over 4k squared. So forget that k. Yeah, 1 over k plus 1 plus 1 over k plus 1 over 4k squared, and this is well, it's bigger than 1 plus 1 over k, for example. Okay, so. Then I can say then that S9 squared is bigger than S6 squared times 1 plus 1 over 6 times 1 plus 1 over 7 times 1 plus 1 over 8. Right? Because here I took k equals 13, 12 squared is bigger than 1 plus 1, 6. And similarly with here. Okay? But this is 7/6 times 8/7 times 9/8, and it's all canceling. So this is equal to S6 squared times 9/6. So somehow S9 squared is just, it's known to be bigger than 9/6. But we can also approximate the other direction, and we say that 1 over 2k squared is less than, again, 1 plus 1 over k, this time I'll get it right, plus 1 over 4 squared. And this is less than, I claim, 1 plus 1 over k plus 1 over k squared plus 1 over k cubed plus 1 over k to the fourth, and so on, all the way to infinity. Why is that? Because, 1 over 4k squared is less than 1 over k times k minus 1. This infinite series here that I substituted here was k over k minus 1, and that's equivalent to saying that 4k is bigger than k minus 1, which is quite obvious. I'm assuming that k is greater than 1. So if k is equal to 1, then I get infinity here, which is certainly less than. So k is greater than 1, and so okay. But this is equal to k minus 1 over k, k over k minus 1. It's just the again the sum of it's 1 over 1 minus 1 over k. So if you take 1 over k to be z in that other formula that I had, this is 1 over 1 minus 1 over k, which is the same as k over k minus 1. So therefore, S9 squared is less than S6 squared times put k equals 6, so you get 6/5, and then 7/6, and then 8/7. So again, the canceling is going on, but now we're left with S6 squared times 8 over 5. Okay, so there's a nice relation. In other words, these Sn squares are fairly tractable, and to summarize what we could prove in general is that S of a plus b squared is less than S of a squared times a plus b minus 1 over a minus 1, and greater than S of a squared times a plus b over a. I'm pretty sure, like I took a equals 6 and b equals 3 in the previous case. So then, even though these S numbers are fairly weird fractions, we can actually get some easy inequalities here. And so what I want to do is prove that all of the inner notches stay inside the circle, all of the outer notches stay outside the circle. Let's go back to the picture of the diagram here. So what are the inner notches? Okay, remind you of that, and then I can draw you the inner notches are the following. The inner notches occur, for example, let's take. Let's see. Can you go back to the computer screen? This inner notch is the x-coordinate is Sn minus 1, and the y-coordinate is S1. and then this one is Sn minus 2 and y and S2 and so on. So so the inner notches occur at Sk and Sn minus k. Okay, back to my formula then. So I really have to take Sk. Here's a point, Sk, Sn minus k. This is a point where the inner notch is, and what I want to show is that this is inside the circle. So that means that Sk squared plus Sn minus k squared, the distance is less than Sn squared. Is what it was. I mean, I could take the square root if that's the distance, but then I might as well square it again. So this is what I want to prove, that the distance, the square of the distance to the inner notch is less than the square of the distance, square of the radius. And well, we just about got it. So I can assume that that k is let's say greater than or equal to n minus k. So then I can use my formula here, and for the less than sign, and I can say that s of k squared is less than or equal to s of n minus k. S of n minus k squared times okay, so n minus k is a in this formula, and so I take the sum of these two guys, which is k minus 1, and down below I take this one, which is n minus k minus 1. It's less than that. And this, in turn, let's see, wait a minute, how did I do this? So let's see, s of k squared plus s of n minus k squared is less than or equal to okay, well, it should be right. Unless I blew it, this is then s. Oh, I'm sorry. Then I got to do Sn squared. So Sn squared. So Sn squared is now I use my inequality again. So n minus k is less than Sn, and so I have to. So here I get n minus k minus 1 over n minus 1, and I have to carry this factor over again. So what I did here is I replaced Sn minus k squared by Sn squared times this fraction by my basic theorem up here, and well, it's canceling again. So this is s of k squared is less than s of n squared, and so now I add the two guys together, and I get the right inequality. Okay, and the other way is actually even the other way to show that the outer notches are. I guess this was the. Sorry. Yeah. This is an inner notch, and I want to show this less. And I also have to show. I have to also show that sk squared plus sn plus 1 minus k. This is the distance to an outer notch is bigger than sn squared. And the calculation is just about the same. In other words, we've got this way to represent two things, and so it's going to turn out that that the squares of the s's turn out to act sort of like linear functions of the subscript, and so it's all going to work out. So there we are, and what I've done is essentially showed you why this formula holds. And it doesn't take calculus much. It's just a little bit of sophistication, but really here we were doing it with geometry, and the thing that Johann found is that really it's because we got a circle here, and that's why pi is arising. Okay, any questions on this part now? Yeah.
This is for two dices. What if there are three dices? Can we extend it to, say, spheres and...
Yeah. Good question. I'm going to get to that. Right. But since you asked it, I might as well show you now. Because although Johann didn't do that in his paper, he found that, let's see if I can, I got a picture from him that he sent me. Yeah, here. You've got to zoom in on this. But here's an example where he takes his, can we zoom in? So again, we got the same thing, but now we got parallelepipeds. You got cuboids, instead of rectangles, and it makes a very nice ball. Okay, so now that gives you the formula for spheres, and also in n dimensions it all works with the right with the right multiples of pi coming in. Yeah, good question. Now, well, a lot more is true, and so I want to go on. What we've done so far then is we've seen why pi occurs in this relation to Sn. Now how do we get that into factorials and stuff? And so let's take a look at this a sub n again, which as you remember was 1/2 times 3/4. And so on, and then we had 2n minus 1 over 2n. And what we've shown is that this is, okay, so I'm going to say what we've shown is that this is approximately 1 over square root of pi n. Why? I jumped a step here, so let's do that slowly. I got Sn was equal to 2n times an, and also I had Sn was approximately the square root of. Okay, so what did I say? We had pi over 4 Sn squared was approximately n, so Sn is approximately the square, Sn is approximately the square root of 4n over pi. So if we divide both sides of this equation by 2n, we get an is approximately 1 over square root of pi n. All right. So in fact, we knew that Sn was pi over 4 Sn squared was actually equal to n plus big O of 1. It's between n plus 1 and n minus 1, which is also, I like to write it as n times 1 plus big O of 1 over n. So it shows the relative error is of order 1 over n. And so what we actually boils down to then, we've shown that an is equal to 1 over square root of pi n times a relative error of 1 with big O of 1 over n in there. Okay, so now a sub n also is a famous number because it arises in connection with the so-called drunkard's walk, or a random walk where you go at every step you flip a coin and you either move to the left or to the right with equal probability. And so we take a walk of n steps, and another way that you think about it is that suppose you're flipping a coin and you gain $1 every time you get heads, and you lose $1 every time you get tails. So it turns out that an is the probability that if you flip a coin 2n times, it's the probability that you come back exactly balanced, exactly the same number of heads as tails. Why is that? The probability that we have the same number of heads and tails is 2n choose n divided by 4 to the n, or divided by 2 to the 2n. If we flip a coin 2n times, then how many of those times, how many of the cases, 2 to the n possibilities, have exactly n heads and tails, and that's sort of the definition of binomial coefficient, 2n things taken n at a time. So that's equal to 1 over 2 to the 2n times 2n minus 1 down to 1 divided by n down to 1 and n down to 1. But now it turns out that's exactly what an is. Then we got to divide this out. But that's what an is, because we can say an is equal to 1/2 times 2/2 times 3/4 times 4/4, and so on until we get to 2n minus 1, and we throw in another factor, 2n over 2n. We just multiply by 1 in here. But now what we've got in the numerator is 2n factorial, and in the denominator I've got n factorial squared times 2 to the 2n. So this is equal to 2n factorial over n factorial squared times 2 to the 2n. And so that's what an is. And so what we've shown here with this argument is that, lo and behold, the probability that we have a balanced sequence after 2n flips of a coin is very close to 1 over square root of pi n, and the relative error is that. So I decided, okay, let me show you what happens when we flip a coin, let's go back to the computer now. Took a bunch of coin flips. I decided instead of using a random coin, I would use pi, because that's the point of this lecture. And so so let's consider the binary digits of pi over 4, and see what happens and so here I go up. It starts with a 1, 1, 1, 0, 1, 0, 0, 1. I got a jingle for remembering this if you want to know. But anyway, so okay, so it goes up, up, down, down, up, down, and so on. And it looks a little bit like the stock market too, as you see here. In fact, people think that pi is supposed to be random, but let's see. It returns back to 0 again. I think after 6,300 steps or something like that before it comes back. Yeah. The next. Anyway, it definitely, the zeros are winning for quite a ways after this. But it's a typical random walk, and the formula that we proved. You remember that we proved that a is the sum of ak times n minus k is equal to 1. So this is the same as saying that the summation of binomial coefficient 2k choose k times binomial 2n minus 2k minus over n minus k divided by it is equal to 4 to the n. It turns out it's equivalent. The formula that we proved for the a's is equivalent to this formula, and that's kind of interesting because it says that you take any random walk of length 2n. There are 4 to the n possible. There are 4 to the n possible ways to do it, and it turns out that that's equivalent to doing 2 balanced walks. So imagine a walk that you're going on a plane, and you start out and you go either east or west, and you go two k steps that are either east or west, and then after you finish going east and west, then you take the remaining 2n minus 2k steps, then going either north or south. Then that's and then you say you got to get back. You got to get back home. So the number of steps where you're going always east or west, and then always north or south, and then but you insist that you first do the horizontal and then the vertical. The number of steps back to the origin is exactly the total number of every random walk can be written as somehow a combination of 2 balanced random walks. Now that's interesting because a lot of a random walk is also a sequence of zeros and ones, and we can encode any sequence of so we can code any sequence of 2n bits as 2 sequences that are balanced, where the number of zeros and ones are possible. This is kind of interesting because a lot of people are using graphical examples of bitmaps these days. We got, my wife just got from the airplane, and this was on her boarding pass, and then there are these kinds of visible codes that people are using, and even more common I've been seeing now, it was on one of the things I bought today for Christmas, was this kind of a pattern that people can read with their cell phones, and it's easy to check. Now, so there's a way of putting bitmaps then into these patterns, and you don't want to have it so that the bitmap is all white or all black. You'd like to have it sort of balanced between white and black. But you still want to be able to handle an arbitrary pattern you still want to have 4n bits, and so in a way this gives a kind of a perfect balanced code. And in fact, there's a real simple way to prove this combinatorially, which is what I want to show you now with the computer. Can we go back to the computer? Let's see, Jason, have you got the okay. Please give me the computer now. The picture. There must be a way for me to push a button and say, okay. So here's our walk again. Oops, what happened? I'm sorry. I've drawn the coordinates badly, and somehow it went down. Okay, well, I put a little error there, but okay. Imagine that I've got a blue line going all the way. I left out that blue line on the horizon. Okay, so what I've done here is I take an arbitrary sequence of in this case 100 bits. These are the first 100 bits of pi, and I'm using pi just as an example, not because it's pi. I want to show you how to map this into a balanced pattern. And down below is going to be a set of 2 balanced. There'll be a value of k, which says that the first 2 k steps are balanced, and then the last 2n minus 2k steps. 100 minus 2k steps are also balanced. And so what I have to do is start with any any pattern of zeros and ones and convert it into a pattern that has the same number of zeros and ones up to 2k, and then the same number of zeros and ones after 2k. And the theorem, the identity says that in fact this is going to be a sort of a perfect encoding, that there's going to be always a way to do this, and a lot of people have thought of ways to do it, but I think this is by far the simplest, and it's the following. You first, the place where the dividing line occurs is the last place that you hit 0. So in any sequence, it starts at 0, and then it has a certain last time that comes to 0, and it's right here after 32 steps. And then what I would have to do is take the rest of it that starts at 0 and never ever touches 0 again, and convert that into a balanced path. And so there's got to be a simple rule that takes us from anything that never gets back to 0, and converts that into a balanced path, and conversely any balanced path to one of those things that never comes back to 0. And okay, so the way I do it, as I'm doing it, if we zoom in here, we'll see that I actually changed these guys to red if it was the last time coming through this row. So the last time on the third row, this is red here. Here's red here. I put a red guy here, and so on. And so now what I do is, after this transition point, I change some of the red guys that were going downwards and make them go upward. And the rule is very simple. And now I show you back on the pad. So here we have a path that starts at 0 and never comes back to 0 again. So here it's going negative and it's never coming positive. So any such path starts out with a downstroke, and then it goes and waves around a while, but never comes up to 0 again, and gets finally to the last time at this level, and then it goes down again, and then there's a down period, and it comes here, and it goes and so on, until finally it ends at some place here, minus 2m. So what I know is that these parts never, they start and end here, and they never go up. So I have essentially m of these things, and what I do is I simply change it so that it instead of going down, it goes up, and I do that for the first m of them. And the last m keep coming down. So then I'm going to have something that looks like this. It's going to go up, and then it's going to come down, and it's going to end up balanced. Okay, so very simple. If I found out that in this case I wound up, I think, at minus 10, and so I converted 5 of these red guys from down to up, and that was that's the mapping that makes a perfect map, a perfect way to balance any path of length 2m. Now, the last thing I want to mention is that this is all tied in with something I lectured about in the 9th Christmas tree lecture some years ago, where we talked about the Christmas tree pattern. And let's see, the fastest way for me to get the Christmas tree pattern is probably to go here to the Japanese translation. No, this is Hungarian. Okay, so okay, the Christmas tree pattern looked like this, yeah, can we get it on there? Okay, this is the Christmas tree pattern of order 8, and we can zoom in, and it looks a little bit like a Christmas tree from afar. But when we zoom in, it's just patterns of 8 zeros and ones, and the idea is that all possible bytes, all possible 8-bit combinations appear somewhere in here, and the ones that are balanced are in the middle. All the middle guys have 4 ones and 4 zeros. Everything that has 5 ones and 3 zeros is in this column. And the mapping that I just showed you for how to show that there's as many paths that never get back to 0 as are balanced, it turns out to be a very nice special case of this pattern. And I think possibly Professor Wada in Japan is watching this lecture now, and I got to show you the Christmas card that he sent me last year. Let's see, we zoom out here, because I got this from him last year for Christmas. What he done is he took the Christmas tree pattern on order of order 6. And then he did the I Ching, the characters for the I Ching, and arranged them instead of zeros and ones in this pattern. So this was a nice present from. He's the man who is in charge of translating my books into Japanese. So this Christmas tree pattern turned out to also be a nice way to prove that identity about binomial coefficient. Okay. Now I'm running over time, so I got it. But I do have one more thing that I got to show you, and that is that the method that we use for showing pi also not only does it give 3 dimensions, as the guy mentioned, but we can do other things, so instead of having circles, we can also consider a superellipse. People know what a superellipse is? So the circle is defined by the equation x squared plus y squared equals r squared, but a superellipse is x to the alpha. Let's say 1 over alpha plus y is 1 over alpha equals r to the 1 over alpha. And I write 1 over alpha because the case alpha equals 1/2 is the case that corresponds to a circle. And so you might say, what happens, for example, if alpha is equal to 1/3? And so in other words, consider the equation x cubed plus y cubed equal r cubed. Then instead of circles, you get something which I can show on the computer. This is the picture that corresponds to x cubed plus y cubed equal r cubed. And what are the coefficients, the a's in this case? In fact, instead of being 1/2, this guy is 1/3, and this guy is 1/3 times 4/6, and then times 7/9, and so on. So we start out with 1/3. In general, we start out with alpha, and then we go to alpha plus 1 and alpha plus 2 for this general superellipse. And the area now is not going to be equal to. You have to figure out what's the area of the brown guys, what's the area of the yellow guys, and so on. But that formula also turns out to be easy. And if we had more time, we could work it out. But I'll just state the results now. And the answer that we get is the following. So the area. Okay, so we have the same formulas as before, and almost all the argument almost works without change. Generalizing from alpha equals 1/2 to arbitrary alpha works pretty much without change. A sub n is somehow minus alpha, choose n, times -1 to the n. And the S sub n is equal to -1 minus alpha, choose n, -1 to the n. S sub n, instead of being equal to 2 alpha, S sub n is n over alpha times a sub n instead of 2n a sub n. And then then we have b sub n, which is the area of a particular strip, a0, a1, up to an a0. That b sub n was equal to 1 in the previous case, but in the pi case. But in this case, it's equal to 1 minus alpha over n minus 1 to the n. And then the area of the rectangle, instead of being n, is the sum of is b sub 1 up to b sub n minus 1. And that turns out to be n minus 1. Well, okay, in the case alpha equals 1/3, it was n minus alpha over n minus 1. Or I could convert that into a formula like the other guy, which would just be, I think, 2 minus, or what is it, 2 minus alpha? I have to, I'm not sure, I'm sure of this formula. Pretty sure. Anyway, so and it all boils down, instead of saying that that we've got a formula for pi in terms of these rectangles, the rectangles now approach a superellipse beautifully, and so we get the formula for the area of the superellipse. X to the 1 over alpha plus y to the 1 over alpha equals 1 is it's equal to 2 alpha times the gamma function of alpha squared over the gamma of 2 alpha. This is, so anyway, gamma function is like a factorial. When alpha is equal to 1/2, gamma of 1/2 is the square root of pi, and gamma of 1 is equal to 1. And so this turns out to be pi. But in general, then the whole argument also proves things that somehow without calculus related to the gamma function. Any questions? Yeah.
1 minus alpha 2n instead of over n.
You know what I really ought to do is be careful about this. So what I have is a sub n is the coefficient. A sub n is somehow the coefficient of 1 over 1 minus z to the alpha. It's the coefficient of z to the n in this. And so then S sub n is going to be the coefficient of z to the n minus 1 in 1 over 1 minus z to the alpha plus 1. And then b of n is going to be equal to the sum of that. So this is going to be over 2 alpha. It should be 2 alpha, really. When I said 1 minus alpha, it should have been 2 alpha. I was thinking 1/3, and twice 1/3 is 2/3. So, and so then Tn, which is the sum of which is the area, is actually then 1. It's 1 plus 2z, the coefficients of this. So it's actually 2 alpha gets in there instead. That's why the 2 alpha is here. Yeah. So the anyway, in order to calculate the area of a superellipse by calculus, you have to evaluate an integral that I didn't know how to. I mean, are you good at integrating the cube root of x plus 1 minus x? X cubed plus 1 minus x cubed. The integral from 0 to 1 of this. That's it turns out to be 2/3 times gamma of 1/3 squared over gamma of 2/3.
So
Yeah.
the original original motivation was this like root pi that came up in the asymptotics for Catalan numbers, which I guess comes from Stirling's formula. I was wondering if you couldn't use this sort of argument to prove Stirling's formula combinatorially.
I didn't hear.
Oh, sorry. So so the original motivation was this root pi in Stirling's formula, basically.
Right.
I was wondering if there was a way to prove Stirling's formula combinatorially using like this sort of argument.
Yes. Okay. That's in fact that's one of the that's exercise 9. Okay. In concrete math, it's actually one of the last exercises in the book. And it's a problem that Marco Schutzenberger asked me in conversation some years ago, and it's unknown how to get the whole Stirling formula from this. But we're very, very close. And I didn't have time to go into Johann's. I thought it would take. I didn't think it would take me this long to go through what I had. So I had a lot of other material. But let me tell you what I would have said if I had more time. First of all, yeah, it's a good joke, I know. But the first thing that goes when you retire is a sense of timing. It's not too hard to prove that Stirling's formula, with calculus anyway, it's fairly easy to prove that that n factorial is approximately n over e to the n times the square root of n times some constant. But now, in order to actually, but now I don't know of a real good way to prove that without calculus. But there are some ways where we don't really need it. But if we're allowed to use logarithms, then suppose that the log of n factorial is equal to, say, any polynomial in n and log n. And you can throw in some other functions too, but just suppose, so for example, Stirling's formula says that it's n times log n minus n plus 1/2 log n plus some constant. Okay. This is plus something that goes to 0. So little o of n, something that's negligible and goes to infinity. Okay, well now, but the fact is that suppose I have the summation of a sub ij times n to the I and log n to the j, for example, and I don't even require that I and j are integers. But then we've proved that a sub n which is this 2n factorial over n factorial squared times 4 to the n is approximately 1 over square root pi n. And if you look at this, the only possible formula, the only thing that works is when it's n log n minus capital A n plus 1/2 log n plus some constant, which would make this happen, because otherwise this wouldn't cancel out to give you just a square root factor here. Okay, if we assume though that the function is of this form, then you just plug into this formula and you see that c has to be square root of 2 pi. Now the remaining question is why e? Okay, and I don't have a combinatorial answer to that. There's a long-winded one, but it's not satisfactory. And so I'd love to know why combinatorially. It seems to rely on the best thing I have so far requires arguing about infinite products. So I have to know that the product of 1 plus big O of 1 over n squared converges to infinity. If I'm given that, then I can come up with an argument that explains why, that I can show why E comes in here using some inclusion and exclusion properties and things like that. And the basic thing seems to be equivalent to something like this: that n plus 1 plus 1 over n raised to the n plus 1/2 power is equal to E times with a relative error of 1 over n squared. And somehow everything that I tried in order to get a combinatorial proof requires finding a combinatorial reason why this is true. And so we have to know what E is, and we have to know what, and then we have to somehow show that this is a very good approximation. And I'd love to see a geometric proof of this of this thing, because then we would be close to answering Schützen's predicted problem. Yeah.
Combinatorial proof, but there's another situation which there's a formula involving pi that comes up in the convergence of a series where it's kind of unexpected. The sum of the inverse squares is pi squared over 6, and it's like, what does pi have to do with squares? But
yes, yeah. Johann has a nice proof of that.
So that's straightforward using Fourier series. The Fourier series, and when your original capital A of z was like a polynomial Taylor expansion, which got me thinking about if there's like a Fourier series proof of Stirling's approximation where the n factorial, like you took the log and then that becomes a sum, and then you can use a Fourier series argument.
Yeah, see,
but then you have to take the exponential at the end, which would explain where that e comes from.
We wanted to minimize trigonometry. We wanted, so what I like about Johann's proof is that you don't need sines and cosines even. So, but we did need to calculate sk squared plus sn minus k squared. But that was done with real simple inequalities somehow. Yeah, with enough tools we can do it. I mean, Stirling did it, in 1730, before, 100 years before Fourier lived. But this way of doing it shows the connection with circles that otherwise you get from some integral, like a beta integral or something. It seems to me. So now. Yeah, I wanted to say something else about that. Let's see. Oh, yeah. There are also other combinatorial problems. Like, suppose you have a random map from the set of integers 1 to n into the same set. So you have f is some mapping, and so then you start out. You say 1, f of 1, f of 1. And so on, and you keep on repeating this until you get a value for the second time. Now, the expected time, the number of steps that you do this turns out to be, I think it's like 1 plus 1/2 the square root of pi n or something like that. I mean, there's something, square root of pi n comes into this formula. This is the case where I don't see why there's any connection to circles yet.
Question.
Yeah, question over on this side.
Can I go?
Yeah.
Okay, so you mentioned random walks earlier. Thinking about a random walk as two balanced random walks.
Yeah.
So I'm curious, how close can you get the lengths of the two balanced random walks?
Well, in fact, if you look at the distribution of k, it seems that the extremes are having k equals 0 and k equals n are the most common. And then it gets it goes like, I think it's something like the square root of k times the square root of n minus k, or no, so the square root of k over n, it's something like this. The probability distribution of k is something like 1 over square root of x1 minus x, something like that. In other words, when x is 1/2, it's the least common case, and when x is at the extremes, it's the most common. When you apply any of these transformations, it turns out that it's not. It's least likely to be in the middle, where I draw the line between the two balanced things, but still not that unlikely. It's like 1 over square root n or something like that. Anyway, the distribution of k is highest at the ends, but but you have to integrate it over two n steps, over n steps, n plus one step. Actually, I came up with a better code for balanced codes some years ago, easier to decode, where you take. I have a paper that came out of I don't know, 30 years ago where I have n 2 to the k information bits and k parity bits, and so like if k is 8, then I have 264 bits, and I come up with a balanced. Give me any byte, and I can give you the corresponding balanced set of 264 bits that represents that byte. Again, a simple, easy to code and easy to decode, and it's probably better. If I wanted to transform this other one, I have to send a balanced set of bits, and then I have to somehow tell people what k is. That's okay. K doesn't have to be. K is small, so it doesn't have to be balanced. But in this case, the whole thing was balanced. Yeah, there's lots of questions come up around this that are quite interesting. I think that's why I accumulated so much stuff to say today. Yeah.
Where'd you get the shirt?
Well, they're like, oh, the shirt is made by a Laotian woman who died a few years ago, but her daughter discovered my daughter on Facebook a week ago. I know I got a whole bunch of people from Facebook in the front row here, so I can mention that. But my wife gave it to me as a Christmas present some years ago, and I traditionally wear it at this lecture. So, yeah.
I can't stop thinking about that last question you posed with the period of the permutation group. What were the conditions you placed on F? On the last sheet that you had written.
The conditions that I place on F is the probability it's random. So it's n to the n possible functions. N to the n f of 1 can be anything from 1 to n. F of,
F is a permutation.
No, it's not a permutation. It's a mapping. I'm saying if I have a random mapping, when do I get into a loop? If f is a permutation, then it might be that I have to go through everything. But if f takes everything into 1, then I'm stuck right after the second step. So you see what I mean? In fact, there's a great computer algorithm based on this. If you want to, if somebody says find you're given a table of n numbers from 1 to n, and somebody says, what's a good way to find two elements of the table that are equal to each other? And the answer is you start at the first one, and if that's 5, then you go to the 5th one, and if that's 8, then you go to the 8th one. If that's 3, and you keep on going until you come to something twice again, and then you've found these two things. And it's only taking you about square root of pi n steps before you found two elements that are equal in this array. And this is true if the mapping is random. But in the worst case, you'd have to look at everything. And it might be that it's a permutation in which case there aren't any. But you would discover that too. Yeah.
When you were mapping the walks onto balanced walks, you never mentioned how you can map back and how many extra bits you need to add.
Oh yeah. So I had these 2m triangles, right? And I moved everything up by m. So then you look at your balanced walk and you see how high does it get, and that's m. And so then you can figure out what the red guys are. This time you go from the left instead of from the right, and that tells you which 5 to lower down. Yeah, very good question. You're entitled to one of these books. Well, thank you all, and have a Merry Christmas.